Loss of control remains one of the primary causes of aircraft accidents. But why do pilots lose control of their airplane, and how can we prevent loss of control? Turning base to final is where loss of control often occurs. You're slowed down, setting up for your landing, you enter a turn, sometimes a steep turn. Your eyes are mostly looking at the landing spot and not the airspeed indicator or the ball. The stall horn can be drowned out by radio communications and engine noise, and turbulence can mask the subtle aerodynamic warnings the airplane may give. If there was a more positive way to keep the pilot informed of the attitude of the aircraft, then loss of control certainly could be avoided. The current most effective system is the stick shaker. If you get dangerously close to stall, the stick actually shakes and warns the pilot. Unfortunately, these systems can be expensive, complicated to install, and linked directly to the elevator control. Another shortcoming is they only convey imminent stall angle of attack. There is no slip or skid signal. The reason these systems are so effective is that they use tactile feedback to signal the pilot. It does not matter what the eyes are looking at or if auditory warnings are drowned out. The pilot feels his angle of attack. What are the two primary reasons for loss of control? They are failure to maintain an angle of attack below stall and uncoordinated turns. If the pilot stalls the wing while in a skidding turn, the plane will rapidly enter a spin without enough altitude to recover. When I was a student pilot, there were two things my instructor emphasized. Actually, he shouted at me, "Watch your airspeed, watch your ball." His intensity and volume conveyed to me that these two aircraft attitudes were not to be taken lightly. So what would be the ideal system for helping a pilot avoid loss of control? As the stick shaker system has proven, it is tactile feedback. What if the tactile feedback system not only conveyed angle of attack, but also slip and skid? And what if it was affordable, easy to install, very easy to learn, and did not take away control like the stick pusher? Imagine a control grip that through tactile feedback gave you all this information through the sensitivity of your fingertips. That invention is here, and it is called the FeelFlight grip. The FeelFlight system consists of three components: a small angle of attack sensor mounted on the pitot tube, or an inspection cover plate, or on the wing, a digital control module mounted on the aircraft panel, which receives input from the angle of attack sensor, an internal slip skid sensor, and for IFR mode, a digital gyro. And then there's the grip. The FeelFlight grip is the true heart of the system and the significant innovation. It has within it 5 electronic solenoids that trigger thrust pins. The first pin signals the fingertip of the ring finger and tells the pilot when he is at best rate of climb. The second pin signals the middle finger for best angle of climb. The third pin signals the index finger to warn of imminent stall. Now, the beauty of the digital control is that the thrust pin signals can be pulsed and varied to provide clear signals. For example, if the pilot continues past imminent stall warning, then all 3 pins pulse with an unmistakable pattern that tells the pilot he must push forward on the stick. Now, what is very significant about the FeelFlight grip is that there are 2 pins that signal slip and skid attitude. These are on the left and right sides of the grip. The reason this is significant is because if the turn is coordinated, then the airplane will not fall into a fatal spin should it stall. Birds fly with such precision. How do they do it? They have the ultimate tactile feedback system. They know exactly what the wind over their wings is doing at all times. With a FeelFlight grip, pilots can now have the same. It is as if you are directly wired to your aircraft attitude. Perhaps we can now fly with the precision of an eagle.